Hi again everyone. In this basic video we're going to look at some simple problems from algebra. In particular we're going to look at three basic problems from a first course in university algebra or college algebra. We're going to work our way through the following three questions. One of them involves the equation of a line in three-dimensional space. The second question involves what's known as the span of a set of vectors. And the third equation involves a system of equations and what's a method known as Gaussian elimination. So we're basically going to work our way through them one by one. The focus of this video is mainly on how to solve the problems rather than the theory behind it. However, I will talk about some important points and write them down as I go through. So let's have a look at the first question. Part I, find the Cartesian form of this equation here. Now, this particular equation, the form of it is in vector form. The lambda here is known as a parameter, and this first entry is a point that lies on the line, and this second entry, the 2 minus 5, 3, is a vector that's parallel to the line. So that gives you some sort of geometric understanding. Anyway, basically to solve this problem, what we do is we eliminate the lambda. So let me show you how we do that. So firstly, a little bit of notation. So this vector x is just the position vector of the point x, y, z. So now what I'm going to do is basically replace this with the column x, y, z, and then I get three equations. So if you look at each component or each entry, we get three equations. So the basic idea is to eliminate lambda to form our Cartesian equation. Okay, so just writing these out, we have, okay, so x equals minus 3 plus 2 lambda, that's the first one. So if I just rearrange, I guess I can just write that out. You probably don't have to do that. Y equals 1 minus 5 lambda. And finally, z equals minus 7 plus 3 lambda. So now let's make lambda the subject in each of these three equations. So let's just rearrange. So this is a z and this is a 3. I know they look a little bit similar, but that's just the way I write. Okay, so let's combine all of these to form what's known as the Cartesian form of the line. Okay, so let's just write these out. Now, you probably don't have to write this in bit, I just like to do it. So this is the Cartesian form then. Okay, so that was pretty easy. In part II, we're asked to determine whether this particular point lies on the line associated with this equation. We're asked to give reasons. So all we're really going to do here is see if this point satisfies our Cartesian form of the line. So that's part I.
Okay, so let's move on to question 1, part II. Here we are asked to consider the following point. And we're asked to determine whether or not this point lies on the equation of the line from part I. Okay, so all we're going to do is substitute each component into I guess each side in the middle of this expression here, and then see if we have equality. Alright, so the left hand side we sub in 11, we're going to get 7. In the middle we're going to get positive 7. And on the right hand side we're going to get 7. So all of these are the same, so we have equality. So our conclusion is our point does lie on our line.
Okay, part 2 involves what's known as the span of a set of vectors. And we're given this set of vectors here, and we're asked to determine what conditions on B1 through B4 ensure that this vector belongs to the span of this set of vectors. Okay, so I guess the first question is, what is the span? Well, if this is a set of vectors, then when we talk about the span of the set of vectors, we mean all linear combinations of those vectors. So let me write this down, and we'll see how we solve the problem. So just to simplify some of the notation, I'm going to let boldface be this vector here, and we're going to let S be the set of these 3 vectors here. Now you probably don't have to write all this down, but what I'm writing down now is designed to help you understand what we mean by the span of a set of vectors. Okay, so let's say this first entry is V1, V2 and V3. Alright, by being the span of this set of vectors, we mean that this vector B can be constructed out of a linear combination of these vectors here. So there are some real numbers, lambda 1, lambda 2 and lambda 3, such that we can write this vector B as a linear combination of these 3 vectors. Now, just to keep things in a geometric perspective here, let's say we had just 2 vectors, and we talked about the span of 2 vectors. Now, the span of 2 vectors is just a plane, and to say that B is equal to the span of these 2 vectors means that B lies on the plane associated with these 2 vectors, V1 and V2. Anyway, back to the question. What does this actually mean? Well, we can write this as a equation involving a matrix. So if I denote this lambda, this vector lambda by lambda 1, lambda 2, lambda 3, this is just a lambda equals b, with a equal to a matrix whose columns are just these particular vectors. Now I'm just writing down v1, v2, v3 to save some space. Alright, so that's basically the theory of the question. How do you actually solve it? Well, it comes down to looking at the well, there's two ways of doing it. That basically both methods involve analysis of an augmented matrix. So I'm going to show you in detail one method, and then I'll give you a quick glance at the second method. So the first method that I'm going to show you is the following. So we're going to look at the augmented matrix consisting of A, the matrix A and the vector B. So it's just the following. And what we're going to do is row reduce this just using row operations. Now the reason that we're going to do that is because we want to see when this particular equation has solutions lambda, and we can do that using Gaussian elimination and row reduction. So what we would like to do, let's look at the matrix as it stands. We've got a 1 here, and what we're going to do is make all of these entries below it 0. So all I really need to do is add multiples, or add or subtract multiples of the top row to the other 3 rows. So in the second row, I want to add 2 lots of the first row, and that'll become 0. I'll add 2 lots of the first row to the third row, that'll become 0. And I'll take away 6 lots of the first row to the fourth row, and that'll become 0. So to make sure I show that I understand what's going on and make my arguments very clear, it's important to write down your row operations. So let me write them all down. Incidentally, it makes it much easier to mark if you're doing an exam or something like this, if you write down all your row operations. So row 2 is going to become row 2 plus 2 row 1. Now some people write equals here. I like to put an arrow instead. And row 4 is going to be row 4 minus 6 row 1. So let's have a look at this. So the top row doesn't change. So if I add 2 lots of this row to this row, that's going to become 0. I'm going to get a 1 minus 2 and b2 plus 2b1. Okay, if I add 2 lots of this row to this row, the first entry is going to be 0, then I'm going to get a 2, then a minus 4, sorry, and then here I'm going to get b3 plus 2b1. And finally, row 4 goes to row 4 minus 6 row 1, so that's going to be 0. That's going to be minus 15. That's going to be 30. And b4 minus 6 b1. Again, don't get confused, that's a 6 and that's a b. Okay, I know they look very similar. Okay, well, what do we do now? Well, if we look down diagonal here, we've got a 1, so let's try to get these two to zeros by adding multiples of the second row to the third row and the fourth row. So I can make that to a 0 by taking away 2 lots of row 2 from row 3, and I just add 15 lots of row 1 to row 2 to row 4. So let's write that down. So the method here is very algorithmic, and you'll get the more problems you do, the easier and the quicker you'll get at it. Okay, so row 3 is row 3 minus 2 row 2, so that's 0, that's 0. And all I need to do is worry about taking away 2 lots of this with this, so that's going to be following, and then here again 0, 0, and oh, we're going to get 0 there as well. Now we could have actually predicted that by seeing that this third row is actually a multiple of the, here is a multiple of the fourth row. So again, using my simplification, I can get the following entry. Okay, so we've reduced it, but what does it mean? What sort of conclusion can we make? Well, in order for this problem to have solutions, and actually there'll be an infinite number, we need to have zeros here, okay, a whole line of zeros. So the system is solvable if this has a 0 and this is 0. So let's make our conclusion. For B to be in the span of S, we require this entry 0 and this entry 0. Okay? So that's one way that you can solve this problem. Let me show you another way. Basically, instead of analysing this and writing this as an augmented matrix, what you can do is consider this where you've got coefficient matrices on both sides, and then write down this particular augmented matrix where you've got the identity on the right hand side. Now, if you do that and then row reduce, so you've got a larger matrix here. If you row reduce using the same steps that I just showed you, you'll get these numbers in here, and just think of these as coefficients. So again, you've got zeros here, zeros here. In order for the system to be solvable, you'd want zeros here. Now, if you interpret and zeros here. Now, if you interpret these as coefficients, well, this line you would need minus 2b1 minus 2b2 plus 1 b3 equals 0, and similarly with the second line. Now, that's exactly what we had in the first method of solution. So there's two good solution methods. You should use which one you feel more comfortable with. Okay, so on to the last question. We've got a system of equations here, 3 equations and 4 unknowns. Find the general solution by setting up an augmented matrix, performing Gaussian elimination, and solving by back substitution. So we're given a definite method there. Essentially what we're going to do is take the coefficients, write them as a matrix and augment it with this, writing this as a vector, and again follow their advice and row reduce and then back substitute. So let's consider the augmented matrix. So here I'm going to form A from the coefficients of each of the variables, and B is just going to be this written as a vector. Okay, so let's row reduce. Alright, so you look here, you've got a -1, here's non-zero, so let's work on getting the entries below this -1 into 0. So if I take -5 of row 1 away from row 2, this becomes 0. And if I add 3 times row 1 to row 3, this will become 0. So let's do that. Right, so that's going to become 0. Next entry is going to become 1, 2, 2, and 2. Then this one's going to become 0. And we get a -2 there. -4, -4, -4. Now, you can see here, these are multiples of each other, and so when we try to get this to a 0, all of these are going to become 0. Okay, so let's work on getting this to a 0. You would add 2 times the second row to the third row. Okay, so that's going to become 0, 0, 0, 0. Okay, so where to now? Well, this is our row reduced form. What we have to do now is do back substitution, but in order to help us simplify things, I'm going to let the variable x3 be lambda and x4 be mu. Okay, here's just parameters if you like. Now the second line tells us that x2 plus 2x3 plus 2x4 equals 2. So I can get an expression for x2 just by rearranging that and substituting in for x3 and x4. Okay, so alright, so if I just rearrange that, it's going to be 2 minus 2 times bracket x3 plus x4, and with this lambda and mu, it's just 2 minus 2 lambda, 2 bracket lambda plus mu. Alright, so let's look at the first row. First row says minus x1 plus 2x2 minus x3 plus x4 equals -3. Now let's rearrange that and make x1 a subject. That's all it is. So what I can do now is substitute in for x3, x4 and x2. And then it's just simplify the algebra. So let's simplify here. I'm going to get, plus, that's right, I left off the +3. So as far as constants go, I'm going to get 4 plus 3, which is just 7. Then I'm going to get minus 4 lambda minus lambda, which is minus 5 lambda. And then I'm going to get minus 4 mu plus mu, which is minus 3 mu. So here are our expressions for x1, x2, x3, and x4, and we've solved our system. Now, as you can see, I've written down a lot in some of those questions. You wouldn't necessarily be asked to write down everything, because I actually wanted to explain some of the things as I went through them. Now, you also see that the time allowed is 25 minutes. I've taken slightly more than that because I've been explaining while I've been running. But my advice is to have a go at these kind of problems. The way you get good at maths is not by watching, you've got to do it. So have a go, and I hope this video has been